We've talked qualitatively about where we would expect to find constructive and destructive interference when we have two wave sources both applying the same frequency or emitting the same frequency wave. Now let's put some numbers to it. Let's make some calculations, figure out where that would happen if we know the frequency, or if we know whether we have constructive or destructive interference, we can figure out maybe what the frequency is or what the wavelength for those waves would be. So we'll try a problem with each set of information given to us. So let's say we have two speakers here, speaker A and speaker B, that are shown on a coordinate plane, so we can get some idea of positions. And we want to know where along the circle that I've drawn there would we expect to see constructive interference. So we need to find every position there where we would have our waves adding together constructively. So that circle has a radius of 0.5 meters, and we know that for constructive interference we have to have a path difference. That's the difference in distances between A and some point here and B and some point there. The difference in those two distances has to be a whole number multiple of the wavelength. So our first step is we need to figure out the wavelength of this wave we're dealing with. So we know that V equals F lambda. This means that lambda, the wavelength, is equal to the speed divided by the frequency. And here we're talking about sound waves, so the speed is 340 meters per second. The frequency is 680 hertz. So our wavelength is 0.5 meters. Okay, so the first situation we could have here that would give us constructive interference would be if we had some point that was equidistant from point A and from point B. So let's see if we have any points like that. Red here. So all the points on this circle are 0.5 meters away from A. Anything that's 0.5 meters away from B also would have to lie on, well, another circle that has a radius of 0.5 that goes around B. So maybe something that looks like this. Close anyway. So we need to figure out where these points of intersection are, because that's 0.5 meters away from each one of these objects, each one of these speakers. So switch over to green for some measurements. First off, where are these points? Well, if they're 0.5 meters away from each of these, we're dealing with, we can kind of imagine a triangle in here that has this length equal to this length. So right in between there, we'd have half the distance right there, half the distance right here. So this point is going to have an x-coordinate of just 0.75 divided by 2, so 0.375 meters. And I should write that this is meters also. We need to get the y-coordinate, and then we'll have the mirror image for it as well. So this point is going to be that point of constructive interference as well. So each one of these is a little right triangle, these guys right here, and for each one we know the hypotenuse is 0.5 meters. And we know that this leg is 0.375 meters. So to get the y-coordinate, we can just do Pythagorean theorem. So let's say 0.5 squared is equal to 0.375 squared plus y squared. And with that, we'll get a y value of, let's see, 0.5 squared minus 0.375 squared. And I'll take the square root of that answer. I get 0.33, so that's plus or minus 0.33 meters. So this would be the negative 0.33 meters. And then up here, we'll have our 0.375 and a positive 0.33 meters. Okay, So those are 2 points where we'd have constructive interference. Where else? Well, these points were equidistant, the same distance from speaker A and speaker B, but as long as we have a path difference that's 0 or some whole number multiple of 0.5, then we'll be able to have constructive interference at any point like that. So we are 0.5 meters away from A. We could be 0.5 meters away from B like this, or 0.5 plus 1 wavelength, that'd be 1 meter away, or 0.5 plus 2 wavelengths, that'd be 1.5 meters away, and so on like that. So let's do the next one here. We'll say we'll look at a circle that's 1 meter in diameter now. So this is at 0.75, so this circle is going to look something like this. Alright, it's a pretty big circle, so it's going to go off the page, but that's okay. We're only interested in these points right here anyway. Alright, so we know that this distance now is 1 meter, and we know that this distance here is 0.5 meters. Alright, so we need to do a little geometry then to figure out where that's going to be. Now just from the way this is drawn, it looks like we're going to have negative x values, so that'd be a good way to check this. I haven't been real careful in my drawings, so I guess I wouldn't be too surprised if we were off there, but it's a good thing to consider as we're doing our check here. So we've got that 0.5 there from A, and the 1 here from B. And we know that this is a distance of 0.75, so we have all this information about that triangle, but we don't have the right triangle, so we can't just do sine, cosine, and tangent, but we could do law of sines, law of cosines here. If you're familiar with those, those would all work. The other thing that we can do is set this up as kind of a little system of equations, and so either way is probably equally time-consuming to solve for those values. So I'm going to leave that as an exercise, though. Where would these other 2 points be? That'd be a good, some good practice for you to do to finish this up. Let's take a look at our other problem type. We've got 2 speakers that are emitting the same frequency wave. We don't know what frequency that is, but we know they're each emitting the same frequency. And then we know that at point P we hear destructive interference. So the question is, what's the frequency of these 2 speakers? Now, actually it could be a lot of different frequencies there. So in a whole number of multiples of this minimum frequency. So let's look at what the smallest frequency could be for which we'd get destructive interference at that point. So destructive interference, we know that our path difference, that's the difference in this distance to this distance here, the difference there has to be a whole number multiple of the half of the wavelength. So half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, 3.5 wavelengths, something like that. So the minimum frequency is going to occur when we have a difference of exactly half a wavelength. So let's make some measurements here, some calculations really. So this distance, that's going to be the path distance for A, and then, for B. And then this right here, that's the path distance for A. And then we've kind of got a right triangle that leaps out at us here, so I'll just put that in. And then this is a right angle. We know the length of the 2 legs on this, so we can figure out the hypotenuse just using Pythagorean theorem. So this is dA, call this dB. So dB squared is equal to 0.5 squared plus 1 squared. So dB squared is equal to 0.5 squared is 0.25 plus 1, so 1.25. And so then dB is going to be the square root of square root of 1.25, which is 1.12. Okay, so our path difference then, our delta D, or sometimes it's written as delta R, but the difference between these two is going to be 1.12 meters minus 1 meter. It's just this distance minus this distance. So that's got to be 0.12 meters. And that has to be equal to, our delta D has to be equal to 1/2 of the wavelength in order for us to get destructive interference. Again, it could be 3/2 or 5/2 or 7/2 of the wavelength, but those would all be higher frequency waves, so we want the lowest frequency on this one. So that means that the wavelength is 0.24 meters. And now we need to find the frequency. So frequency is equal to the speed times the wavelength. Whoops, got that backward. Speed is equal to the frequency times the wavelength. There we go. So our frequency is equal to the wave speed divided by the wavelength. Wave speed is 340 meters per second for sound and air. Our wavelength is 0.24 meters. And so 340 divided by 0.24 gives us about 1420 hertz for the minimum frequency where we would get destructive interference at point P.